Okay, so we talked about, bless you, you okay? So we talked briefly about selection sort. We're going to now talk about insertion sort, which works a little bit differently, but it's going to have a similar behavior. Sorts the list by moving each element to its proper place in the sorted portion of the list. Okay? I think it makes a lot more sense when you do it on the board. In its proper place. So hold on a second. Let's go to the board. All right. We are going to start with the list. Okay. So first off, is a list of one element sorted? Yes. All right. Good. We can assume one is always sorted. Let's move it to 2. Is that sorted? No. What needs to happen? We need to swap it. So step 1. You go 5, 7, 33, 2, 18, 2, 0, 2. Okay, great. All right, now that we know the first 2 elements are in sorted order, let's add a third one. Is that 33 in the right place? Yes, it is. Yeah, so we don't need to do this one. Yes. 5, 7, 33, 2, 18, 2, 0, 2. All right, so we know these 3 are in sorted order. Let's add the 2. Is it in the right place? What needs to happen? It needs to be moved to the front spot, and then these guys are shifted down. I said shifted down. What does that mean? Yeah, you gotta, inside of an array, you'd have to bump them all over, so that could be an O of N operation right there. So step 3, you got 2, 5, 7, 33, 18, 2, 0, 2. All right, now you know that these 4 elements are in sorted order. Let's add the 5th, 18. Where's that go? Yeah, it goes over here. You got to shift the 33 down. So, oops. 2, 5, 7, 18, 33, 2, 0, 2. All right, so now we know these 4 elements are sorted. We'll add the 5th one. Is that in the right place? All right, so here we go. 2, 5, 7, 18, 33, 2, 0, 2. Okay. I know this can sometimes be confusing, so the slides did give another example, so let's go see what that looks like. So let's say that you have these 4 elements. You are your sorted list so far. You're now going to look at the 23. Where does the 23 go? Where the 25 is, but these 2 elements need to be shifted down. So you need to effectively move the 23 over here. So you want to copy the 23 to a temporary variable. Notice the 23 is over here, because next you're going to overwrite the 23 with the 30, overwrite the 30 with the 25, and then move the 23 where that 25 is right there. So there it is. There's that copy. And then now you want to move that temporary back in there. And now with that temporary in there, you know your sorted list is of those 5 elements. And is that where it ends? Good. Okay, so you know that those 5 elements are sorted. What would you do next? Or what would the algorithm do next? Yeah, take the 17. Where's that guy going to go? 18. So what's going to happen to the 18 through 30? It's all going to be shifted down. You see what's happening? You're building a sorted list with this one. With selection sort, you move every element to its proper location. With this one, you're slowly building a list until it's correct. Okay. All right. Let's do a big O analysis. Okay. How many comparisons are done? So we're going to do comparisons first. Well, on this line, how many things did you compare? 1. How about this one? You did 2 comparisons, because you had to compare the 5 to 7, or you took the 33 and compared it against these 2. So 2. All the way up here, you'd have basically n-1 comparisons. You just compare the 2 and 2 to everything beforehand. Really, you can actually stop once you get something bigger, but I'm just saying worst case in this situation. So do you see how I came up with this quick analysis? All right. Hopefully it looks familiar. It's like selection sort, but in reverse. So hopefully you know what the next answer is. How many of these are we doing? N. All right. So that means comparisons is N times, what's the average here? Over 2. We'll just say N over 2, roughly, which is equal to N squared over 2, which is equal to the big O of N squared. All right. So comparison still N squared. All right. Let me move this over here. I can erase. All right. All right. So now we're not doing swapping, are we? We're doing assignments because we move something and then we assign everything over, right? Right. So I'm going to call it assignments. Okay. How many assignments were done here? Effectively 3, because a full swap requires 3. So we're going to put 3 because you got to copy 5 to a temporary, copy the 7 over where the 5 was, and then copy your temporary back to where the 7 is. So that's 3. All right, here, none. Over here, well, copy the 2 to a temporary variable, copy the 33 over, copy the 7 over, copy the 5 over. That's 4, right? Oh, I'm sorry, and then copy the temp back where the 5 is, so that's actually 5 assignments. Over here, you take the 1, so you got to make the temp, right? Move the 33 over, and then type it. So you got 3. Yep. Here, of course, 0, 0. All right, this is going to be a little hard to do an analysis of because these numbers are jumping around. So let's do worst case scenario. What is the worst case that could happen at each step? So this is the worst case here because you had to move everything over because you had to do 3. But let's say here this 33 you need to go at the very beginning. How many assignments would there have been? 4. 4. This one had to go to the beginning, it's 5. And then this would actually be dot, dot, dot to about, what was it, N plus 2, roughly. I'm going to put some right there. Because notice it's incrementing by 1 each time. You like my sound effects, Barry?
Yeah, I just saw I was saying that. I was like, those are interesting sound effects for like whole estimates.
Okay. So, and then how many times are we doing this? Oh wait, does everyone see where I got this N plus 2? No? So we started with 3, right?
Oh, yeah.
And then you basically, worst case scenario, you're adding 1. I'm doing worst case analysis. So at the end, what would be 6, 7, 8. And then we have, what, 6 elements, so it'd be 6 plus 2, which is what N plus 2 is. So that's how I got my N for at the very end. If we had 1,000 elements, then it would go all the way down. It'd start at 3, but it would end at 1,000 plus 2. So it's just N plus 2. You see where is that better? All right, great. So that's how I got my N plus 2. How many times do we do this? N times. Uh-oh, what's assignments? N times N plus 2. And I'm just going to say that's big O of what? N squared. Oh, man. Wait, huh. So which one is better? Insertion sort or selection sort?
Selection sort.
Yeah, so far selection sort looks like it's winning out. Okay. All right. Well, whoops. Let's but this was for what data structure? An array. This is for arrays. Yeah, the other one was also for arrays. So for arrays, selection sort is better because you don't have to do as many assignments in there. Y'all see where I got that from? Everyone tracking? All right, great. Let's do this for a linked list. You understand why there's arrows now? Because we're using pointers? All right, great. So we're going to implement this with a linked list instead of an array. You start out with 7. Obviously, it's sorted, yes?
This is insertion sort again?
This is insertion sort, but with a linked list. All right, so we're going to have, so let me see if I can help you out. This is actually going to be done differently. That's your array, or that's your, I'm sorry, your linked list. Step 0, you're going to have your linked list, your new linked list, start off with 7 pointing to null. All right, because that's just the first element. And you want to add the 5. Where would the 5 go? In the first element. So 5, arrow, 7, arrow, null. All right, now we're going to have, I'm going to go ahead and put rover over here. Now rover is going to be 33. So you're at the 33. Where does the 33 go? At the tail. Okay. 5, 7, 33, null. All right. And rover is now pointing to the 2. Right?
Yeah.
Okay. Where's it going now? The head. All right, so we got 2, arrow 5, 7, 33, and then rover is what? 18. Let me put my little null at the end of here. All right, 4. So we have 18. Where's that going? 7. Now here's the trick. This is a linked list. So when you want to do a linked list and you need to put the 18 there, how many assignments are really done? Oh, well, 2, right? Because the 18 now needs to point to the 33, and the 7 points to the 18. So you're only doing 2 assignments on worst case. Fix that up real quick. I will erase that to make it a little cleaner. Oh no, that comes out all right. Well, yeah. Let me go ahead and clean that up. All right. And now rover, where's rover? 202. Where's it going? At the tail. Whoops. Go back to my arrays. And then, of course, rover, oops, that's an arrow to null. Rover is pointing to null, so we know to stop. Notice we actually don't care, we don't record the size of the linked list. We just wait until rover is null, and then we're done with insertion sort. Do keep that in the back of your mind when you're looking at this. Okay.
Is that a big deal to not store size?
It can be. It can be it's a big deal when you don't have to know the size, because that simplifies certain situations. Sometimes that's a big deal, sometimes it's not. Okay, so let's do comparisons. How many comparisons were done here? Because you had a 5. How many things you compared it to?
0.
Well, you compared it to 7, right?
Yeah.
You compared it to the 7, so that was 1. Now you're comparing the 33. You had to compare it to the 5 and the 7, so that's 2. You had the 2. You compared it. Actually, you only did 1 comparison, right? Right. So it was just 1. You had the 18. How many comparisons did you do?
3.
You had to do 4 because you had to know the stop when the 33 came. So you had to do 1, 2, 3. Okay, we're done. I can see my 7's looking kind of weird. Let's do this.
Dr. West.
Yes.
Hit your screen for a second.
Oh, it's beautiful. Thanks. Let me fix my 7's for you all real quick, because I bet you that gets a little confusing with all these arrows. How's that? Is that a little better? Okay. Oh, next time, don't say 7, okay? When I ask for a bunch of numbers. All right. So what do we have to compare? Rover here, we had to do it 4 times because we had to compare it against the 2, the 5, the 7, and the 33, so we knew we were done. All right, next, rover is 202. How many comparisons do we do? All of them, which is 5. And yeah, well, actually we're done, so I didn't have to write that last one, but that's okay. Okay. How many times do we do this? N minus 1. I think we only had 5. Technically, we're done at step 5, but yeah, N minus 1, close enough. So for comparisons, this was actually roughly N. Worst case starts at 1, dot, 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 all the way up to N. The length is, or N minus 1, I should say. Because at this time we had to do all 5, and we always had to append to the end. You would always do, 1, 2, 3, 4, 5, et cetera, all the way up to N minus 1. Y'all see that comparison? Okay, great. So what's, or linked list, what's the comparison? Can you just tell me? The big O. O of N squared, because you're doing N minus 1 times N minus 1, right? Or N divided by 2, technically. So it's still O of N squared comparisons.
Technically, at the moment, this is faster than the other ones, but it's N minus 1.
Yes,
Wouldn't it be negligible?
but it'd be negligible for large inputs. So big O only concerns about large inputs. All right, how many assignments did we have to do? Well, let's take a look at that. How many assignments were done here?
What?
Actually, yeah, there were 2. Wait, hold on. No, there's just 1. You moved this arrow to point to that 7 instead of pointing to that 33. That was it. That's all you did. How about the 33? 2.
It's just gonna be
Oh, hold on. Not necessarily. What about the 2? How many did you have to do? How many how many did you assignments did you do? Oh, hold on a second. I skipped 1. We have the 33. Sorry about that. Let me roll back. I have put the wrong numbers in the wrong locations. There was 1 assignment here. There was 2 assignments here. When you added the 2, how many assignments were there? 1. Let's see, and over here we're adding the 18. How many assignments were there? Let's see, the 18 had to point to the 33, and then the 7 had to point to the 18. So that's just 2. And then over here, 202, how many assignments were there? Just 1. So worst case, you have to do 2 assignments each time, which is O of 1. How many times are you doing this? N minus 1. So what's the assignments? O of N.
That's a lot better.
Yeah. Okay. So for an insertion sort, which one should you do? If your choice on your lab, which I'm going to give you, for your lab you may do either selection sort or insertion sort on a linked list. Which one should you do? Yeah, insertion sort. All right, good. I'm glad we had this discussion. If you wanted to do a select, or actually you have to do both for arrays, so we're going to leave it at that. Okay. Now, move that over just a little for the people online. Any questions so far? Okay, great. Let's go make sure we did our big O analysis correctly. The for loop executes N minus 1 times. That's that outer loop that I was talking about up there. Best case, list is already sorted, it's just N minus 1. Worst case, for each iteration, everything that's true, so you got to do it N squared. So average number of key comparisons is N squared, pretty much no matter what. All right, we got that. Oh, good. All right, they put the graph up here for me. So let's go ahead and look at the 2 for an array. Average case for bubble sort for linked in on an array. They don't list it up here, but on an array. Notice that the comparisons and swaps for bubble sort is both N squared. Selection sort, you have N squared comparisons, but O of N swaps. So it's going to be a lot faster. And then insertion sort, it looks like it's going to be similar to bubble sort. And is this all that we're going to talk about today? Yeah? Okay, great. Yes.
What's that?
I told you it was gonna be fast today. Right, so I usually at this point say I've presented 4 different things. I've done selection sort and insertion sort, and then I've presented that they can be done on an array or a linked list. Let's see, which one do y'all want to see? One.
Erase.
Array, which one? Insertion or selection?
Selection.
Selection for arrays. Is that what you want?
What is the main question here? Like, what do we want to
In class, we will go through the one of the algorithms I presented today. We'll code it up. Let me go and pause the video since y'all can deliver.